This is the linear functions and their construction tutorial. Let's begin this tutorial by taking a look at a couple linear functions. Now remember, with linear functions, you're going to be using most often the slope-intercept formula, which is y is equal to mx plus b, where m is the slope of your linear function. And remember that slope is defined by this formula, y2 minus y1 over x2 minus x1, which is essentially saying the change in y over the change in x. Or you may recall this as rise over run. How much does your graph rise or fall over the distance that it runs, left and right? Now I've drawn a couple simple linear functions on the graph to our left. The green linear function you can see is rising as it runs to the right. So this has a positive slope. Whereas the purple linear function is a horizontal line at y is equal to 4. So it's never going to change in terms of its y coordinate. It will always be 4 no matter what the x is. So recall that horizontal lines have 0 slope, whereas a vertical line going straight up and down at any point, has an undefined slope. So remember, if m, your slope, is positive, then the function is increasing over its domain. If m is negative, then the function is decreasing over its domain. So now let's go ahead and take a look at a word problem that'll help kind of jog your memory about linear functions. Sean collects comics, and he has seen an increase in their selling price since the recent popularity of movies based on comic books. Sean has noticed that over the last 20 years, his comic books have risen in value by $1.25 each year from their initial price of $1.75. He would like to create a linear model that will help him to decide how long he should hold on to his comic books to maximize his revenue. So the first question we're asked here is A. Write a linear function for Sean that will express the cost C of each comic book as a function of its age, x. So I know right off the bat we want a function C to express the cost of the comic book as a function of its age, which is going to be our x value. Now consider putting it into our y is equal to mx plus b format, where m is the slope over time and b is our y-intercept. Our y-intercept can be considered the initial cost, essentially, of this comic book, because it's the initial point at which our line enters our graph. So I know that Sean originally paid $1.75 for each of those comic books. So that's going to be our y-intercept. That's where our slope is going to enter the graph. And our x, like we said, is our time in years. So that's what's going to be going across the x-axis of our graph in the near future here. We want to write down that they're increasing each year, they're rising in value each year by $1.25. That rising in value is the key to tell you that that is our slope. That's the rise that we're referring to. For every 1 year, so each year here, we rise in value by $1.25. So we go up by $1.25 for every year that we go over on the x-axis. So $1.25 here is going to be our slope, so 1.25x plus 1.75. So if we graph that linear function, and you can graph that in your calculator if you'd like, this is what it's going to look like. Notice how our graph enters the value here, or our line enters our graph at 1.75. And it continues upward. It's rising in value at $1.25, so it goes 1.25 up for every 1 year that it goes over. Notice this point right here at 1,3. We've gone 1 year over, and now our comic book is worth $3 as compared to the $1.75 when we bought it the previous year. Hopefully by now you can start to see that you could create a function for anything that you may have at home if you look at its current value based on the value of when you bought it. This is the value of linear functions and functions in general, is that we can create mathematical models and we can evaluate things like when we should sell particular items. We can do this for business models, you can do it for science models. It's really a practical function. So now that we've graphed our linear function, the next question is, what is the value of each comic book 20 years after it was purchased? Now you'll notice that our graph only goes up to 10 years. Had it gone up to 20, we could just follow the 20 line on the x-axis straight up until it reached the graph, and then follow that point on the graph over to its y coordinate, and that would be the value of the comic book. However, since our graph doesn't go up to 20, we want to plug in 20 for our x value, because that's our age in years for each comic book. So the cost of our comic book after 20 years will be equal to 1.25 times 20 plus $1.75. Alright, so 1.25 times 20, you can do that by 1.25 times 10, so just move your decimal over 1 to 1250, and then double that to make it 20. So 1250 times 2 is $25. Then we'll add our $1.75 to $25, and that brings us to $26.75. That's going to be the cost of a comic book after 20 years. So some of you might look at that and say that's a good investment. For some people, that's not a very good investment. You could probably find something else that's going to increase in value faster than comic books. Now let's take a look at D. After how many years will a comic book be worth more than 10 times what Sean paid for it? So you got to do a little thinking in this problem. We want it to be worth more than 10 times what Sean paid for it. And since Sean paid $1.75, we want it to be worth more than 10 times that. So if you move the decimal over 1, you get $17.50. So we want it to be worth more than $17.50. So after how many years will our cost of the comic book be worth more than $17.50? So our x value, this value on the right side of the equation, is going to have to be greater than $17.50. So we've got 1.25x plus $1.75. First thing I want to do is subtract that $1.75 from both sides of the equation. So $17.50 minus $1.75 is $15.75. And that's still got to be less than 1.25x. So I want to get our x alone to find the number of years. So I'm going to divide by 1.25 on both sides of the equation. On the right-hand side, that's going to cancel out, and you're going to have x is greater than 15.75 divided by 1.25, which is 12.6. So the number of years Sean would have to wait for his comic books to be worth more than 10 times what he paid for them is going to be greater than 12.6 years. Anything larger than 12.6 years, and Sean has now made 10 times more than what he paid for that comic. Alright, so now we've looked a little bit at linear functions and how to construct linear functions. Now I want to show you how to relate linear functions to data points that you've been given. Here are your basic scatterplot diagrams. Let's take a look at this guy on the left. This one shows a positive correlation between these data points. And it's a positive correlation because if you were to draw a line, and we call this a best fit line, but a line that seems to be the closest to all those data points, it would look something like that. And that line looks like a linear function with a positive slope. So here we would say there's a positive correlation between these data points. Now on the next graph, you'll notice that if we were to draw that best fit line, it would look like this. That's the line that's closest to all those points. And as a linear function, that line would have a negative slope. So we say that there's a negative correlation between these points of data. Now, I can't find a best fit line for these points. It could look something like that, or it could look something like that, or even like that possibly, or even straight up like that. There's a ton of different ways where you could draw a line, and none of them is necessarily closer to all the other points than any other line. So in this case, we can't really find a correlation between these data points. Whatever's being compared here on the x and y axis of this graph, there doesn't appear to be any relationship between those two sets of data. It's like comparing the number of oranges harvested in Florida this year to the number of male childbirths in Alaska. There doesn't really appear to be any correlation between those data sets. Now here you'll notice that if you wanted to draw a best fit line, it would probably look something like this. And in that case, there does appear to be a correlation, however it doesn't appear to be linear. It seems more quadratic in this case. So now that you've reviewed these scatterplot diagrams a little bit more, let's take a look at how we would actually apply one. Imagine you're given this set of data: vitamin C dosage versus number of sick days. And you're asked these questions: to draw a scatter plot of the data, and then whether or not there's a relationship in this set of ordered pairs, and if that represents a function, and then you're asked to interpret the slope of the data. Well, the first thing we want to do is to draw a scatter plot of the data, and we've been told that vitamin C dosage should be our x coordinates, and number of sick days should be our y coordinates. So this would be the x and y of the first point, respectively, on your data plot. So here's what a scatter plot would look like of this data. Notice we've plotted each of these x, y coordinates together. Now the second question is, does the relationship in this set of ordered pairs represent a function? And I would say yes. I would say that you could find a best fit line here. If I were to draw on my best fit line, it would look something like this. That's a line I think that might be the closest to all the different points of data on that graph. And this line, you can tell, is a linear function with a negative slope. So I would say that there does appear to be a relationship here, yes. And I also want to say that it appears to be a negative correlation. So the last question is to interpret the slope of this data. Well, if we have a negative correlation, that means that when one value goes up, the other value goes down. So in this case, as we increase our x value, which is the dosage of vitamin C that these people are taking every day, we decrease our y value, which is the number of sick days they take every year. So I would say that the correlation here says that the more vitamin C you take, the less often you get sick. And that's the slope of the data, what it actually represents in this particular linear function. I hope this tutorial has helped to refresh your memory a little bit about linear functions and their construction.